Okay, one of those first important topics is the concept of mutually exclusive events. Remember when we first mentioned the Venn diagrams, we said that mutually exclusive events can be shown in a Venn diagram, and mutually exclusive events are dependent events. So actually they are the most dependent we can have. So the reason for this is that mutually exclusive, well, first of all, let's define this mutually exclusive events. These are events that cannot occur at the same time. Such as, you already know good examples of mutually exclusive events, such as flipping a coin. The outcomes, head and tail, those are mutually exclusive because they cannot occur at the same time. The same is true with rolling a die. You can't roll a die and get 1 and 2 at the same time, or 1 and 5 at the same time. Those outcomes are all mutually exclusive. Okay, so in terms of probability and the notations we've been using, what does this mean? So first, let's talk about the symbolic form. So in symbolic form, we say, suppose outcomes E1 and E2 are mutually exclusive. Okay, so how do we show this symbolically? Well, we say that E1 intersection E2 is equal to 0. This means that they cannot overlap. If they cannot overlap, that means they cannot occur at the same time, so they are mutually exclusive. Now, events E and 1, E1 and E2, these are general names that I'm giving these events, but you can assume E1 and E2 to be anything. Occurrence of heads and tails when we flip a coin, or occurrence of 1 and 4 when we roll a die, things like that. By the same token, we can build on this kind of symbolic representation of ideas and say, well, if that's true, then the probability of this must also be 0, right? How do we show that? Probability of that outcome is equal to 0 as well. So this is just saying, what is the intersection of these two events? Nothing. It's just nothing, 0. They have no overlap. They have no common element. And this says the probability of that outcome is 0. Okay. How about the Venn diagram? How do we show this using a Venn diagram? Well, this is how. Let me write it here. We can show that in a Venn diagram as E1, E2. And that would be U or sample space. We can call that universal set or a sample space. That's one way of showing E1 and E2 that are mutually exclusive. Another way of showing, but this way of showing it, it means there are other events in addition to E1 and E2 that are out here, right? But E1 and E2 are mutually exclusive. Another way of showing mutually exclusive events with a Venn diagram that is like this. E1, E2. So that means the sample space, let me this time call it S, the sample space S has only two events, E1 and E2, which are, by the way, mutually exclusive. They cannot happen at the same time. If you're in this sample space, you're either here or there. Okay, the boundary line is just a visual help for us to know that these two sets are disjoint sets or mutually exclusive sets. The other thing we should know from this section is something called additive rule. Also known, or AKA, the addition law. So when I studied this in my own textbooks, this is what I saw. This is what it was called. Now it's called additive rule. It makes no difference. It's the same thing. So the first thing I want to say here, and as we approach chapter 8, I want to remind you that random events can be either independent or dependent. So additive rule applies to both independent and dependent events. But the Venn diagram, this applies only to dependent events. Remember that? Applies only to dependent events. Okay, so then what does the additive rule say when we have two events E and F? So suppose, or given, two events E and F, the additive rule is probability of E, that's P's probability, E union F. Notice this whole thing is one variable. It's like X. This is not being multiplied, P is not being multiplied by this or anything. This is just a statistical notation for one set. The set, the probability of union set between E and F, that's what it's saying, is equal to, so this is just one probability value, is equal to probability of E plus probability of F minus probability of E intersection F. Some of you, or all of you, may remember this as a variation of the counting formula. Remember that? N lowercase n E union F equals n lowercase n E lowercase n F minus lowercase n E intersection F. Remember that? This is a variation of that, but this time it doesn't apply to counts as it did with the counting formula. It applies to probability of events. Okay, so you can tell that we're getting deeper and deeper into calculating probabilities. So we talked about mutually exclusive events just now, right? Suppose that we want to modify this additive rule or the addition law for events that are mutually exclusive. Think about it. Or even pause the video. Think about how would this formula change if events E and F are mutually exclusive. How would it change? Pause the video, think about it, and then come back to this video. All right, so I'm assuming that you've done that, and now you have an idea about how this would change for mutually exclusive events. So for mutually exclusive events, this would change to probability of E union F equals probability of E plus probability of F. That's it. Because that piece, the overlapping piece, which suggests that E and F can happen at the same time, would be 0. Right? That piece is 0 for mutually exclusive events. So this is the adjustment of the additive rule for mutually exclusive events, because probability of E intersection F is equal to 0. Okay? So let's see a brief example just to get used to these concepts and how to work them in a formula. So suppose, or if E and F are events of a sample space, and probability of E is equal to 0.4, probability of F equals 0.5, probability of E intersection F is equal to 0.2. Find probability of E union F. Okay, so these notations, just like the part of this problem that is in plain English, these notations, these symbols speak to us. When you are given these symbols, intersection and then union, you already know that these are associated with the additive rule. So then use that. So probability of E union F would be equal to probability of E plus probability of F minus probability of E intersection F. We're looking for the union event, the probability of it, the probability of E union event, not the union event itself. So that is equal to probability of E, which is 0.4, plus probability of F, which is 0.5, minus the intersection probability, which is 0.2. So 0.9 minus that, we get 0.7. Again, probability values should be between 0 and 1. If you end up with values that are outside of range, in that range in your calculations, then you should review your steps to see where you may have miscalculated something. Okay? So let's do another example. Watch the symbols. The symbols are speaking to us. So right there you have a union intersection. Your mind should immediately remember the additive rule when you see these two symbols together. We will have more symbols coming up, and that's a good way of connecting formulas to these calculations. And here we want to find probability of F. Okay. Well, again, these two immediately connect to the additive rule or the addition law. So let's write that down. Probability of E union F is equal to probability of E plus probability of F minus probability of E intersection F. By the way, like anything else in algebra, you can manipulate this formula algebraically. You can move this to the other side and make this coefficient negative. You can move this term to the other side and make the coefficient positive, and so on. You can bring this to this side and on and so on and so forth. So let's see. Once I see these two symbols in a problem, that tells me that I should use the additive rule. And then I'll plug in and see where that takes me. So that's union, that's 0.6. Probability of E, we are given as 0.4 right there. Plus probability of F is not known, so I'm just going to keep it that way, minus probability of E intersection F, which is 0.1. Okay, so this becomes an algebraic problem, right? So move everything to one side. 0.6 minus 0.4 plus 0.1 equals probability of f. And therefore, so this is 0.3. So probability of f is equal to 0.3. All right. I'm sure you have questions on the discussion board. We will go over those. So let's see another example. So what is the probability that here we get to a phrase that is extremely important in this course? The phrase "at least." We've already seen one example application of one application of this, that at least one of the refunds is issued by direct deposit. Okay. So remember on this last exam that you just took, there was a problem where you had to just read the problem and translate it into a maximum problem, right, with the objective function and the constraint inequalities. So here, we're translating this to the probability notations or symbols that we've just discussed. So union, intersection, probability of event, this, that. We want to do that before we can solve this. But it's not different than what we've been doing in that exam or in the previous sections. So for example, it says in 2009, the IRS reported that 62% of tax refunds for the 2008 tax season were issued through direct deposit. If two refunds, right, they're talking about two refunds. So let's give this life with symbols. So we want to say R1, and we want to say that refund 1 issued through direct deposit. deposit, right? And let's take refund 2 as refund 2 issued through direct deposit. So again, we're introducing variables, which is a way to give life to what you read in plain English in mathematical terms. Okay? We're recreating this problem mathematically. All right. So then it says, and if 2 refunds were selected at random, let's R1 and R2 would do that. The probability that both were issued, see, take note of these important phrases, that both were issued by direct deposit is that. And they're talking about probability. Probability of both happening through direct deposit is 0.49. How do you give life to that statement in mathematical terms using the notations we've talked about so far? That's what you should be thinking about. Well, we learned that probability, that's P, and we just assigned those refunds variables. So parenthesis, refund 1, it's talking about both of them, something that happens to both of them. So refund 1, intersection, refund 2. That's how we translate in this context, probability context. The intersection is a translation of the word both. So probability that refund 1 and refund 2 were issued through direct deposit is 0.49. Then what is the probability that at least one of the refunds is issued by direct deposit? At least translates to either R1 or R2 or both, right? Doesn't it? At least means either R1 was issued through direct deposit or R2 was issued as such or both. That's at least. So that then tells us that what we're really looking for in symbolic terms, so we want to give life to that statement in mathematical terms. So that'll be probability that a refund 1 union refund 2 was issued through direct deposit. That's what we are, the question is asking about. What is the probability that at least one of the refunds is issued by direct deposit? So they're asking for the union event. Okay? So, and one thing that we haven't yet translated into mathematical terms is that first sentence that said the IRS reported that 62% of tax refunds for this season were issued through direct deposit. So we need to give life to that in mathematical terms. Let's do it this way. So that would be probability of refund 1 having been issued through direct deposit is 0.62. By the same token, probability that refund 2 was issued through direct deposit is also 0.2, right? That 62% is, if you pick any refund from that tax season 2008, the probability that it was issued through a direct deposit was 62%. Today it's probably much higher as more people have, or more employers have direct deposit, or the IRS is set up to do this with more people. As people are trusting the direct deposit way of receiving the refunds more, the probability has probably gone up. Okay, so now once you do this translation of information from plain English to symbolic form, then look at your symbols. You are given information about the intersection. You are asked to find the union. What do these two tell you? They tell you to use the additive rule, right? That's the only formula where you have those two symbols represented. So we know that probability of refund 1 union refund 2, according to the additive rule or the addition law, is equal to probability of refund 1 having been issued through direct deposit plus probability of refund 2 minus probability of refund 1 intersection refund 2, right? That's the additive rule. Just keep in mind, how do we get to this point? We get through this point by translating the plain information from plain English to symbolic form for this context. And then noting that we have intersection and union, then the additive rule is a natural connection that we make between that and the formula. Okay, so we're looking for this piece on the left, and probability of R1, we already know it's 0.62, plus probability of R2, which is 0.62, minus this intersection probability, which we were told is 0.49. So we do the algebra on this, and we get 0.75. Okay. One, I can't emphasize more to you that when you see this, at least the question is asking for the union event. Okay. So let's see another example. Okay, so here we have a case where there are two types of vehicles, a 12-year-old GeoPrism and a 1-year-old Toyota Sienna. And on any given morning, the probability is that, well, right there, let's give these variables, right? Let's give this information life in mathematical terms. So for the GeoPrism, I would pick, we can pick G, so G for the to represent GeoPrism, and T for the Toyota vehicle. Okay. Then, on any given morning, because once you introduce the variables, then you can attach information to them. on any given morning, the probabilities that the vehicles start are 0.98 for the Sienna. Let's attach that information. So for the Toyota Sienna, or let me add that for the Toyota Sienna, it's probability that it starts on any given morning is 0.98 for the Sienna and 0.84 for the Prism. So this one, probability of this is 0.84. If the probability is that at least, that phrase again, right? Remember what that represents? The union, because at least means either Geoprism starts or the Sienna or both start. That's the definition of the union event. So this means Geoprism union Toyota. If they're talking about probability too. So I need to put a P right before these and put these two in a parenthesis. So there's a P right there. P, probability of the Prism union Toyota starting. One of the vehicles will start is 0.9968, and that's the union event. They're telling us the probability of the union event. So probability that G union T is equal to 0.9968. Okay. Then what is the probability that they both start? Now that last question should be easy for you to translate into this kind of symbolic form or notation. They're talking about the probability of both starting. So what are they asking us? They're asking us to find probability that G intersection T will happen, right? They both start. Well, you have the union event notation, you have the intersection, so they're asking you to apply the additive rule or the addition law. So let's do that. Probability of G union T is equal to probability of G plus probability of T minus probability of G and T. Remember we said the additive rule is used with both independent and dependent events. This is a case of applying it to independent events, right? So each car starting or not starting is independent of what happens to the other car. Okay, so the union event is given to us, that's that. This one, probability of G is 0.84 plus that 0.98 minus the unknown piece, which is probability of G intersection T. So this is just a matter of solving for the unknown, right? We can move this to the other side. It becomes probability of G intersection T equals and becomes positive, right? It was negative on this side, positive. Move this to the other side. So 0.84 plus 0.98 minus 0.9968. So after we do all the algebra or the arithmetic, we should get 0.8232. So this is the probability of both vehicles starting on any given morning. So this is calculated to 4 decimal places. Remember, probability values you calculate should be between 0 and 1. If they're outside of that range, you have made an error. You need to retrace your steps to see where the error is. Next topic, we've already mentioned this, but your book mentions it again, and I will do the same. And it's good to be redundant and keep these things forgotten or not quite yet addressed. So it's better to address these in a solid, repeated way. So we've talked about complementary events. So now we're going to talk about probability of complementary events. So suppose that probability of E represents probability that this event E occurs, that event E occurs. And also suppose that probability of E bar, I put the bar with a different color so it catches your eye, but it's E bar, that probability that event E does not occur. Okay, does not occur. Then, if that's the case, then probability of E plus probability of E bar is equal to 1. And probability of E is equal to 1 minus probability of E bar. They're the same thing. This is the same formula as that, but this has been algebraically manipulated. This relationship, especially for those of you who are already taking Econ 261, you already know why this is so important. Those of you who will take it in the next semester or future semesters, you'll see how important this is. It makes calculations of probability extremely much more easier than if we didn't use this. In some ways, it makes them possible. When you think about if we didn't use this, we would have to sit here and consider too many events. It would take up so much time. So this is a very useful, easy to understand, and very useful relationship to keep in mind between any event and its complement. Okay, so let's see one example of applying this. But the reason I bring up Econ 261 is that in this course we use a little bit of this in our calculations, just a little bit, not too much. But in Econ 261 you should see full applications of this to various situations. So here's an example where we can use this relationship. And let me add that we want to, in this calculation, we want to disregard day and year. Okay, so here is that phrase again, at least. So this is referring to the union. In some other situations here, it just means that if you have 6 people, how many ways can at least 2 of them were born in the same month? I mean, if there's so many different ways of approaching this, and the easiest one would be to use the complement of this. That means find out how many possibilities are there for none of these people to have been born in the same month, right? Consider the complement of this. In how many possibilities are there such that none of these 6 people were born in the same month? Then subtract it from 1, and you find exactly what this question is asking for, which is at least 2 of them were born in the same month. So let's do that. We're going to find out. So we're going to find out what is the probability, or in how many ways, how many possibilities are there, and its probability of none of these people having been born in the same month, right? So, first of all, let's calculate in how many ways can these 6 people, could they have been born in any month with no restriction, right? So we have 6 people. So we want to calculate the 6 individuals having been born in any month, right? No restriction whatsoever. Okay, how do we calculate that? Very easily. We already know about the multiplication principle. Remember that? So 1, 2, 3, 4, 5, 6. Individual number 1, number 2, well, how many ways could this, how many months could this person have been born? 12, right? How many months for this person? 12, right? In any month. Notice, in any month. 12, 12, 12 for all 6 by the multiplication principle. Multiply all of these together and we end up with this number, 2,985,984 possible ways that we could have surveyed these people, and the 6 could have given us answers in how many in which month they were born. These are how many possible ways they could have been born, taken as a group, taken as a as the 6. Okay, so now we want to know what is the so this is all possibilities, all possible outcomes, all possible outcomes. Now let's find out the scenario where no 2 of these people were born in the same month. How many of that can there be? So calculate no one is born in the same month as the other. Okay, so let's go back to the multiplication principle again. So we have 6 possibilities, right? 6 individuals that each of them has a different possibility for having been born. So if we're calculating no 2 are born in the same month, then for this individual, there must have been 12 options to be born in, right? But as soon as we pick some month, suppose this person was born in March, right? Then this person could have been born in any month but March. So we have only 11 possibilities for this person. Then 10, and so on, 9, 8, and 7. So multiply all of these together, and we end up with 665,280. Right? That's the number of that. Now we can find the probability that no 2 are born in the same month. So probability that no 2 people from this group in the same month, right? So it's simply a matter of taking the ratio of this number by that number. I'm going to show the answer up to 4 decimal places, like that. Is that the answer we want? Is that the final answer? No, right? This is the probability that no 2 people from this group were born in the same month. But we're looking for at least 2 people that would have been born in the same month. That means at least 2, that means maybe 3 of them. We also want to know that. At least 4 of them were born in the same month. 5 of them born in the same month. And we also want to know the probability of all 6 having been born in the same month. So to get that probability is the complement of this probability. So all we have to do is subtract this from 1. So let me do that on the next page. So now, let me title this with so the probability that at least 2 were born in the same month. All right? So we say, so 1 minus 0.228, and we have 0.772 as the probability of that. All right? So that's a very useful demonstration of why complementary events, that rule that probability of some event plus probability of its complement is always equal to 1. Why that's such a useful rule. And again, those of you who will be taking or are already taking Econ 261 already know how important that rule is. Okay, let's see another example. So this time we have a 6-sided die that is cast. And the question is, what is the probability that we have an outcome that is at least, again that phrase, right? At least 5. Okay. So we're casting this, let's see, how many times does the problem tell us? No. It doesn't, okay, so we have that cast. What is the probability that we have an outcome that is at least 5? Okay, so a 6-sided die, what is the sample space for a 6-sided die? We already know it's 1, 2, 3, 4, 5, and 6. We also know that in a sampling space like this, all the outcomes are equally likely. In other words, probability of 1 equals probability of obtaining 2 equals probability of obtaining a 3 equals obtaining a 4, a 5, and a 6, and all of that is equal to 1 over 6. We know that. Each outcome is equally likely. So at least 5, let's translate that. Let's translate that to symbolic form. So that'll be probability that the outcome is at least 5, so greater than or equal to 5. That's what the question is, right? Less than or equal to 5, that would mean these two events, right? So what is this equal to? Probability that the outcome is equal to 5 plus probability that the outcome is 6. So the probability of this outcome is 1 over 6. The probability of this outcome is 1 over 6. So we have 2 over 6 or 1 over 3 as the outcome. Okay, so that's another. And if you want to give the answer in decimal form, then depending on how many decimal places does the question allow or wants you to give the answer to, so you can say either that or say up to 4 decimal places right there. So we can give the answer in that form as well. Let's see another example. Tying the next game. And the question is, what is the probability that the team will lose the next game, right? Okay, so here this is a demonstration of the sample space again and what it has to do with the complement of events. So suppose Chicago Bears football team has this much probability of winning, tying, and then at the end they ask us about the probability of the losing the game. So let's give these variables. Winning, let's take that as W, right? So winning and tying with T and losing with L. And they're talking about just the next game, right? So this is not their overall stat here, but this is just about whoever the next is the competition next, that's the probability of these events occurring. So the sample space of this game, the outcome for this game, next game, has 3 possibilities, right? So it can be, so here's the sample space. They could win it, they could tie it, or they could lose it. That's the 3 possible outcomes in the sample space. They play the next game 1 billion times, the outcome is not going to be any different than one of these that are already listed in the sample space. That's what a sample space is all possible outcomes, no matter how many times they play each other. Okay, so because we already said that the probability of the outcomes in a sample space, if you add those probabilities, they should add up to 1, right? So we already know that probability of winning is equal to 0.65. Probability of tying, or T, is 0.05. So they're asking us to find the probability of losing the game for this team, right? So we know the whole thing should add up to 1 because it's part of the same sample space. So probability of W plus probability of T plus probability of L should be equal to 1. Therefore, we have 0.65 plus 0.05 plus probability of L should be 1. So probability of losing the game for the Chicago Bears football team is add these two, subtract from 1, or 0.3. So there's just 30%, or I shouldn't, well, it's just 0.3 for probability. The question has come up, is probability the same thing as, well, the question is can the probability be represented as a percentage? Yes. Are they the same thing? No, because percentages can be over 1, right? If you say 200%, that means 2. But probability can never be outside of 0 or 1, out of those bounds. So can the probability value be represented as a percentage? Yes. Are the two the same? Is probability the same thing as percentage? No. Okay, I hope that answered that question as well. So let's use another example which uses a Venn diagram. So here we want to use using a Venn diagram to find probability. So suppose we have an example where it says that given this Venn diagram, okay, let's draw that. So we have two circles like this overlapping, and the sample space like that. So let me just say capital S for sample space. Let's say the probability here is 0.8, 0.47, 0.25, and this is 0.2. So we add these, we should get to 1, and we do, right? So given this Venn diagram, part A, it's asking us what is the probability of either A, oh, I forgot to label these circles. So this is circle A, B. And what is the probability of either A or B? Well, first, let's translate this to symbolic form. What is it that they're asking us? Do you remember what that phrase translates to? Either this or that or both, which is implied. That should bring to your mind the symbol of the union, right? Either this or that. So probability of A union B is what they're asking us. Now, what is probability of A union B? Well, probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Remember the additive rule? Great. So now let's plug in. Probability of A is not just this, it's the whole thing. So it's 0.25 plus 0.08. So this 0.08 is shared between A and B, but it's part of A as well as part of B. Plus probability of B, so that would be 0.08 again, plus 0.47. Notice that we added the 0.08 twice. So we have to omit or get rid of the duplication by subtracting it once. So minus the intersection A and B, which is 0.08. Okay, so if we do the algebra on this, then we get 0.33 plus 0.55 minus 0.08, and that is equal to 0.8. As probability that either A happens or B happens or both. Notice or both here is not given, but it's okay. It's implied. It's implied in that language used in probability. In probability, when you say either this or that, implied there is that both is part of that question. Okay. So then we can ask, what is the probability of neither A nor B? Or let me ask the question in both ways so you're familiar with both language. What is the probability that neither A nor B occur, i.e. The probability that none of the two events occur. You might receive both kind of language in a question, either in homework on an exam. Well, this probability is the complement of that, because this probability, what did it represent? The probability that either A or B or both happen. But neither A nor B, that's the complement of that. So then we can easily say that's probability of A union B bar, this bar means the complement of A union B, is equal to probability of, it's equal to 1 minus probability of A union B, right? Because it's a complement of A union B. So 1 minus 0.8 is equal to 0.2. Okay, so I'm sure you have questions. Let's go over those during the discussion board. So again, this section continues with really important ideas and concepts. The next one is when we want to compute. So far we haven't talked about odds, but now we will. Computing odds given probability values. And then after this, we'll talk about computing probabilities given odd values. Okay, that's how this will go. So the best way to approach this problem is just jump right into an example. So let's do that. Suppose that the probability of winning a game is 0.36, right? And we want to find the odds in favor of that language. You have to take note of this, in favor of winning the game. Okay, so if we know that probability of winning this game is 0.36, then the probability of not winning that game, that is W bar, right? Again, I'm using the red ink to draw your attention to the difference in notation there. So probability of winning is 0.36. Probability of not winning is 1 minus that, right? So 1 minus 0.36, or that is 0.64, right? So this is 0.64, winning and not winning. So if we want to find the odds in favor of, then we'll take the ratio of probability that we will win this, that winning a game is that by the probability of not winning that game. If we were looking for probability of losing this game, we would we would flip this. So then probability of W bar would be divided by probability of winning. So whatever we're looking for, whatever odds we're looking for, is in the numerator, and the complement is in the denominator. This time we're looking for in favor of winning. So 0.36 divided by 0.64. Let's simplify this. So multiply both numerator and denominator by 100. You get this. Simplifying this further, we get 9/16. That is not the odd. That is not the odd. So the odd is when you write it in the proper form. The odds are in favor of winning the game is 9/16 to win. Those are the odds to win. Okay. So let's do okay, so that gives us an example for computing odds given probability. Let's then give an example of computing probability given odds, given the odds. So we're reversing what we did in the above. So we have some formulas to use here. If the odds in favor of E are A to B, right, like that. If the odds in favor of some event were given like that, A to B is just to generalize those numbers. A to B, then the probability of E can be given this using this formula, A over A plus B. So this is in favor of divided by A plus B, the summation of those, and that's going to convert this odd into probability of in favor that E will occur, or the probability in favor of E. You're converting the odds in favor of E to probability of E occurring, and that's the formula to do it with. Then if the odds against E are given, in other words, you can be given odds in favor of something or odds against something. Either way, you should be able to convert that odds into probability value. So if the odds against A, so let me write that with different ink color, and against E are A to B, then probability of E, so we're calculating the probability of E in both cases, but in one case we were given the odds in favor of E, in the other case we were given the odds against E. Okay, so we're calculating probability of E in both cases. Okay, so this time we take the ratio of B not A, B divided by A plus B. So that's the formula for that. One example of this which would make this evident very, very quickly is this example. So we say if the odds in favor of getting a 4 on roll of a 6-sided die are 1 to 5, or 1 to 5, either this way or that way, then what is the probability of getting a 4? So we're given the odds, we want to calculate the probability for it. Well, that's just simply probability that we get a 4. It's 1 over 1 plus 5, or 1 over 6, which we know that to be true, right? I picked an example so we could quickly connect it with which what already we know. We already know. Okay, so having said that, these last two examples are extremely important. So one, it says, given that events E and F are independent events, and that probability of F equals 0.84 and probability of E intersection F is equal to 0.221, we want to find the odds against E. Okay, if we want to find the odds against E, remember we have to know the probabilities of E occurring and E not occurring. So we want to know the probability of E bar and probability of E. Well, one thing that we haven't yet talked about, now it's a good time to introduce that concept, is that when events are independent, this formula is applicable. So probability of E intersection F is equal to probability of E times probability of F. Very important formula. But remember, please, this only applies to independent events. Many, many times people lose points because they apply this to independent events. This problem is clearly telling us that the events are independent, so we can use this formula. Okay? So look for clues to use this formula. And so we're looking for odds against E, so we need probability of E and that E hasn't occurred. Well, how are we going to find out probability of E? Because right now we know probability of F and E intersection F, but not E. Well, fortunately, the events we are told are independent, so we can use this formula. So let's just plug in. 0.21 is equal to probability of E, which we want, times probability of F, which is 0.84. Well, that means probability of E, probability of E occurring is equal to 0.21 over 0.84. So this will give us 0.25, as I found out. Okay. Now quickly, if probability of E is 0.25, then what is the probability of E bar? By now we know that very quickly, right? It's 1 minus 0.25 or 0.75. So what are we now know probability of E from this formula because E and F were independent, and we know E bar, which means E is not occurring. So they're asking us for the odds against E. That means odds that E does not occur, right? We want that. So that means we have to take the ratio of probability of E bar that does not occur over probability of E, that E occurs. So the odds that we're looking for tells us in which way to calculate this ratio. If it was asking for probability of or the odds against in favor of E, I would divide probability of E by this. So I would flip this. But the question is, what are the odds against E? So that's probability of E not occurring. That's against E, right? E is not occurring, divided by probability that E occurs. So E not occurring was 0.75. Probability of E was 0.25. So after simplifying, what do we get? We get 75 over 25. Simplify that, we get 3 over 1. Is that the odds? No. Don't leave the answer like that. The odds are 3 to 1 against E. Okay, I hope that makes sense. So let's see another example. This one, we're not dealing with independent events, but we're dealing with mutually exclusive events. These two last examples are pretty critical, and they're the culmination of everything we've talked about in this section. And so given that event E and F are mutually exclusive. So in the previous example, I boxed the word independent, because that was the key clue for us as to what formula to use, which we introduced that formula there as well. And now this time it's for mutually exclusive. E and F are mutually exclusive. That's again a big clue to us as far as which approach we should take to solve this problem. So if E and F are mutually exclusive and probability of F is 0.36 and probability of E union F is 0.8, we want to find the odds in favor of E. In favor of E. Remember, the last one was independent. The events were independent, we were told, and we looked for the odds against E. Here, we are told that the events are mutually exclusive. Remember, mutually exclusive events are the most dependent events you can possibly have, because they can't happen at the same time. If one happens, that means the other one is not going to happen. That means they're very, very dependent on each other, right? Independent events, on the other side, they do whatever they want. And one happens, maybe the other one happens, maybe it does not. But that's for independent events. Mutually exclusive events are very dependent, and they cannot happen at the same time. Okay, so now, because we know that the events are mutually exclusive, then we know that probability of E union F should be equal to probability of E plus probability of F, right? We know that because the probability of E intersection F drops out from the addition law or additive rule because it is equal to 0. That's the, well, let me add that right immediately after this. Because probability of E intersection F is equal to 0 for mutually exclusive events. Okay? So mutually exclusive events, that means the overlapping part, the intersection part, is equal to 0. I might put this on exam 3 as a question, which you will see, which you will take through Canvas. Okay, it'll be an online test. I'll put it on Canvas and you'll take it there. I might put this as a question. Okay, I might. So because of that, because that term drops out, then the union event is equal to probability of E plus probability of F, just 2 terms. Well, let's see, if we want to know the odds in favor of E, we need to know the probability of E. So it's critical for us to know this probability, which we don't yet have. Okay, so let's plug in. We know that probability of E union F is 0.8. Probability of E is unknown, so I'm just going to leave it as that. And then plus, sorry, I didn't mean to mix this with that. Well, let me put this here. So 0.8 equals probability of E plus probability of F, which from the problem statement should be 0.36. We'll solve this for probability of E, and we get, what do we get? We get 0.8 minus 0.36, or probability of E is equal to 0.44. So we want the odds in favor of E. That means if you know probability of E, then you know the probability of its complement. So if probability of E is equal to 0.44, then probability of E bar, that means E not happening, must be equal to 1 minus 0.44 or 0.56. So that's the we are looking for odds in favor of E. Now we have the probability of E and the probability that E does not occur. Probability that E does occur, probability that E does not occur. That's E bar. Because we're looking for odds in favor of E, then the ratio that we take must be that of the probability that E occurs divided by the probability that E does not occur. Does not occur, with that bar shown on top. Okay, so probability of E is 0.44. Again, whatever you're looking for, the odds in favor of something or against something, that probability is in the numerator. You divide it by the complement probability in the denominator. So in this case, 0.56. And then let me continue here. So let's multiply both numerator and denominator by 100. So we get 44 over 56. Simplify this with 4. So we get 11 over 14. Is that the odds in favor of E? No. This is going to tell us how to write it. So the odds in favor of E are 11 to 14. And this is in favor of E. I cannot emphasize this language. I hope this being a video, this has I mean, the disadvantage here is that you're not, as I said earlier, you can't ask your questions right away, but hopefully with this being a video, you have the willingness to go back and review these videos again and again until you catch up with how important these phrases are. Again, odds against something, odds in favor of something. Hopefully this being a video helps you catch those little things that are hidden in the context of all this calculation we are doing. Mutually exclusive events. What happens when we have mutually exclusive events? What happens when we have independent events? All of this we covered. I mean, we just introduced a very useful formula here on my previous slide for independent events. And this is very, very important, that we can find the intersection probability if we know the events are independent. Sometimes we are told that independent. Sometimes we can, from the context of a word problem, we can assume that they're independent. That would be a judgment call. Cases like that are not complicated at all. So it should be easy to determine. Okay, so with this discussion of computing odds given probability and computing probability given odds, we are wrapping this discussion of section 7.5. When we come back in the next video, we will talk about the expected value, which is another topic in chapter 7. That would be section 7.6, which is coming up next.